Hello everyone and welcome to this next lecture. Today we'll be looking at genetic programming, which of course is another evolutionary algorithm. And this time we are evolving programs. So let's get started. Now, genetic programming can be seen as a specialization of genetic algorithms. The main distinction between GPs and other EAs, and also of GAs in particular, is the representation used. Most other EAs uses things like vectors, strings, bit strings to represent the solution. GPs, on the other hand, uses trees. And since it uses trees, the reproduction operators are also different. So this includes both crossover and mutation. Now, this was initially developed by John R. Corza to evolve computer programs where the program output was used as a measure of fitness. Now, genetic programming algorithms evolve executable computer programs where each individual or solution or chromosome represents one computer program. And each of these is a tree structure. And the reason for this is when we work with computer languages, when a computer language gets translated into machine code, it first goes into a translation phase. And one of those phases is where it gets converted into an abstract syntax tree. So somewhere in the line during the compilation or interpretation phase is you need to get to this AST or abstract syntax tree, and that then is then translated into whatever language or machine language you want at the terminal level, or of course if you interpret it directly. And that's why we use a tree structure to represent our programs that evolve. Now, since we're using trees, there's two important implications. The first is, of course, you've got adaptive individuals. Now, GAs and most other EAs for that matter have a fixed size representation usually. So in other words, you've decided you've got a 20-dimensional problem. There's 20 variables that needs to be optimized, and it's fixed in that way. GPs, on the other hand, they evolve over time, and they may come in all kinds of different sizes. They could be very deep, they could be very shallow, they could have a very broad branching factor, so that also comes into play. The point is, you've got different sizes of solutions. And then secondly is, since we're working with abstract syntax trees, you're going to need a domain-specific grammar. Now, what is that? Your grammar defines the language and the valid instructions in your language to solve that specific problem. And any solution must adhere to that grammar. Otherwise, you literally have a syntax error. So that is what the grammar is for. So these two things, adaptive individuals and a domain-specific grammar. Now, the grammar is typically defined as a context-free grammar, or a CFG, using notations either Backus-Naur form or extended Backus-Naur form. Now, so for example, let's say you've got an agent that must evolve to play tic-tac-toe. You could have something like this. We're going to start right at the top. This is where it starts. A program is going to be an expression. Okay. And then an expression could either be a move or an if statement or a log or a arith or a constant and so forth. And let's have a look at move, for example. So move could say it starts with the word move and then again open bracket and closing bracket and then some expression in between. That expression, of course, again can be a move or an if or something like that. If statement over here consists of an if, then you've got an expression again, then a second expression and a third expression, and then of course there's brackets around those three expressions and so forth. So this defines how the agent or how a valid program would look for an agent that's playing tic-tac-toe. And this is of course unique for every kind of problem that you're trying to solve. Now let's have a look at an example of how a program might look that follows this grammar. Okay, so here's an example of an evolved program. And of course, this is very limited. The idea is that this is going to keep on evolving and try to get better. But the point is that this is already a valid program according to the defined grammar. So how does it work? It says, okay, there's an if statement. And then the first part in the if statement checks E square for empty. So this is the center square. So if you look at your tic-tac-toe, I'm going to do a very bad drawing here. So that, of course, is 0. That is 1. This is 2 over here. Then 3. And then 4. 5, 6, 7. And, of course, 8 is right over here. So the idea is that if 4 is empty, you're going to move there. That's what it does. Move in position 4. That's where you place your move. And, of course, you could then argue as part of the grammar that once you've made your move, you exit the program immediately. Otherwise, this is the else part. If 0 is empty, so we're going to check this square over here. If that is empty, move there. Otherwise, move in 8. So this program can only move into these 3 squares. So it's very limited. But the point is, it's valid. And of course, it's a start, because usually the center square is the best. And of course, then you should prefer a corner if memory serves. And of course, this at this point doesn't really check if 8 is empty. So we're going to assume that there's an arbiter that's going to make sure that only valid moves are allowed. And if you make an invalid move, then you are penalized. But the main idea is this is your grammar. And using this grammar, we can evolve an abstract syntax tree capable of playing tic-tac-toe. Now, you might be asking whether genetic programming is still relevant. You know, in light of modern LLMs, transformer-based code generation tools, things like ChatGPT, Claude, Copilot, etc. Now, the answer to that, of course, is absolutely yes. Genetic programming uses a process of evolution to find niche solutions to very specific problems. And of course, LLMs are not built for that. LLMs generate generic code based on a large corpus that has been fed to it. And it won't necessarily be able to optimize a very specific solution to a very specific problem. And because with evolutionary programming, there's no existing data, with an LLM, you need that corpus to train it beforehand. While with genetic programming, it is able to discover those niches itself. It's able to evolve the code to actually solve that problem. It's driven by that fitness function. So it's 2 totally different techniques, and each have their specific domain where they totally flourish. So yes, we need both of them. So let's quickly have a look at the initial population. So just like any EA, we need to start somewhere. Now, the initial population is also randomly generated within the restrictions of the maximum depth and semantics. In other words, you're going to define a maximum depth. You might and say you can't exceed this depth, and also the semantics. In other words, the grammar that you've defined. You can't exceed or you can't change the grammar. The language must adhere to that grammar. So you can't just generate random trees. It's also possible to start very simple, in other words, small, and then only keep on growing the moment you can't make any further improvements. So you can go with both these approaches, but very importantly, it must adhere to the grammar. The grammar is very important. You cannot generate a tree that is not adhering to the defined grammar for the problem that you're trying to solve. Now, just like any other EA, we need a fitness function. Now, the fitness function for genetic program tends to be very problem specific. And it can sometimes be quite difficult and complex to define because there's usually very steep cliffs and canyons. What do I mean by this? The idea is that sometimes a very small change in the program, maybe just a sign that changes or an if statement that's omitted, can have huge effects on the actual execution of the program. So it can sometimes be quite difficult to define a fitness function that's able to make continuous improvements to actually solve the problem. But if you do it carefully, of course, it can be done. Now, how is this typically, how's the fitness evaluated? The program needs to be executed. So some kind of interpreter is going to execute that abstract syntax tree or that tree, and we're going to look at the output that this actually delivers, and we're going to evaluate that against a series of test cases. Okay, and it's important that these test cases must cover all aspects of the input domain. So in other words, you can't leave something out because then the fitness function or the program will not be guided to solve that specific part of the problem. You need your test cases to cover the entire input domain. So every input, what do you want for this? For every input, what output do you require? You could use both an absolute and a relative fitness for this. So let's say you have you're evolving a tree to basically mimic a certain equation. Then, of course, you know exactly what the result of that should be, so you can use an absolute fitness function. But if you have that tic-tac-toe that we've just seen, that could be relative because you're going to get the agents to play against one another, and the best agents would be allowed to survive. So you could use both absolute and relative just with GAs, because GPs are, in fact, of course, a specialized form of a GA. And then also you could penalize solutions for if it's very deep or very bushy. In other words, you could try and guide the algorithm to prefer smaller trees. And that is your fitness function. Okay, so let's quickly chat about the crossover function. Now, any of the standard selection strategies can be used. So you could use, like we've seen with rank-based, tournament, proportional selection, random perhaps to some degree, but any of those selection strategies can be used. And now that you've selected the two individuals that's going to participate in reproduction, how do we do crossover? Now, there are two typical techniques, and they're very similar. The one, of course, is creating one offspring, and the other one is creating two offspring, where you actually select parts of the trees and you just swap them around. So let's quickly have a look at an example of that. So here's parent 1, so here's parent 1, here's parent 2, and you then randomly select, two parts in the tree. So for parent 1, we've selected this node over here, and for parent 2, we've selected, let's make this one green. There's parent 2. For parent 2, we've selected this part in the tree. And then, of course, in this case, we're creating two offspring. So over here, you'll see this part of the tree over here, all the way up to here, is, of course, parent 1. That's that part of the tree. And then, of course, we take this part of the green parent, parent 2, and that, of course, gets added over here. Okay, and that forms the first child. And then for the second child, you'll see we use this part of parent 2. There it is. And then that part, the sin 3 times 4 times A is, of course, from parent 1. This is this part over here. And this way, you create two children or two offspring from two parents. And, of course, if you do one child, you would basically then just do the one part. But, of course, to keep it symmetrical, you can very easily create two offspring from two parents in this fashion. And that is how crossover is defined. There are, of course, some important design considerations. So from your grammar, okay, first of all, so from your grammar, each non-terminal, so the left-hand side that we've seen, so program is expression is could be a move, all of those. This typically becomes a possible subtree, and that's going to be that internal nodes, okay? So keep that in mind. Each one of them could be a potential subtree. Keep your grammar operations as simple as possible. Okay, so in other words, rather make the operations complex, but the syntax, keep that as simple as possible so that it's easy to evolve complex operations. And also remember that not all grafts are viable. So it might not be possible to combine trees, just randomly swapping subtrees around. It might not be valid. So for example, let's say you've got a square root, you can't add things in there that's, for example, negative to the square root, then it's going to break. You might already handle that at syntax level. So just be cognizant of the fact that not all grafts are viable. So if it's not a viable graft, you may need to select other parents or select other parts in the tree in order to facilitate that crossover operation. Now, just with crossover, mutation is also a little bit different because we're working with trees, and there's quite a number of them. You could have a function node mutation. So here, any non-terminal node, so a function node, could be randomly selected and replaced with a function of the same arity. In other words, a plus could be replaced by a minus, but you can't replace an AND operation, a Boolean AND operation, with a not, because an AND takes 2 and a not only takes 1. So you have to be careful to replace them if they have to be compatible. You could have a terminal node mutation. In other words, at the leaves, you can change one of those to something else. So maybe a 3 can become a 4, or a variable like a or x could become a number, something like that. You could have a swap mutation. So with swap mutation, select any two nodes and then just swap the actual internal node, not necessarily the subtrees. That's the children. And of course, in this case, you again have to be very careful that the arity is actually preserved. And then if we look at the next few ones, so we could have a grow mutation. So with a grow mutation, a terminal node is randomly selected, like the 3 or the 4 or the a or the variable, and it could be replaced by a randomly generated subtree. That you could do. You could have Gaussian mutation, where a terminal node is selected from a set of nodes, and that represents a constant, and that constant value can then be added by adding some random value to it. And then you also could also have a trunk mutation. So with a trunk mutation, a function known as randomly selected and replaced by a random terminal node. So this is the opposite. When you grow the tree, here you trunk it. So in other words, if you have a sin 4.5x, for example, you can just replace it with x. And that's, of course, also a form of mutation. There's also a number of asexual operators. Now, it's for one parent that's defined. So you could have a permutation operator. Now, with this is similar to the swap mutation, but here you take a function and you take all its nodes or its children nodes and you give them a random permutation. So, yeah, and of course, you can also apply this to mutation as well. There's also an editing operator. Now, with this, you basically simplify the tree. So let's say you have something like x and x. And of course, the Boolean operator x and x, that of course can just be x. So you could simplify the tree to make it more simpler in this way. So that's known as the editing operator. And then a very cool one is known as the building block operator. Now with the building block operator is you identify useful functions in the tree. It could be that you find that for your entire population, let's say you've got 100 trees in your population, there's a certain function that appears in all of them. Maybe you're doing Boolean logic and you haven't defined an XOR function. And then building block operator could identify a tree that looks exactly the same. This part of the tree is over here, and it's also replaced or duplicated in all the other functions or all the other trees that are also very fit. And then you can extract that, make a function of it, and then just use that function as part of the possible non-terminal node. So you literally allow your grammar to evolve with your trees. And of course, that is really cool, because now you've got evolution of evolution, sort of. You can actually extend the languages. And of course, later on, that function that you've extracted could again be part of another function that gets extracted. So a building block operator of building block operators, along those lines. But these are known as the asexual operators, which are also defined for genetic programming. Next, of course, we've got building block genetic programming. Now, this is a very simple concept. The idea here is okay, and this was specifically developed for decision trees. Okay, and decision trees, of course, they tend to grow in complexity depending on the problem that you're trying to solve. So the first population in your genetic programming process, your first population, consists of a root and terminal node. So the smallest possible tree that you can have. Now, if evolution can no longer improve these trees, in other words, your decisions doesn't improve, the fitness simply doesn't increase, then of course you start applying a grow mutation. So now grow mutation is allowed to be switched on, and for a number of iterations you can actually increase the tree size. And then of course you switch grow mutation off and you repeat this process. And now it tries to evolve it further. Can we improve the decision tree? Then you're going to hit a ceiling again. Can't improve it any longer. Then you enable the grow mutation, and this tends to steer the algorithm in a direction so that you can get an optimal result for your decision trees. And this is a very good technique. And of course you might wonder why can't we just use the normal training method for decision trees? Again, remember that with genetic programming, this is a very useful technique when you don't have data available. So in other words, you can't test it against a known data set. But let's say you've got an environment where you can at least evaluate how good it is. Then, of course, a genetic programming is an excellent way to train decision trees. Now, the Santa Fe problem is a very nice case study or academic problem for genetic programming algorithms. Now, the idea here is that you've got a whole bunch of artificial ants, and they have to search for food pellets, and the only thing that guides them is this program that evolves over time. And they have very, very small, simple actions that they can follow. They can only look in front of them one square, and then they can turn around, and they have to be able to search and find as many of these food pellets as they can. Now, a YouTube video that I quickly want to show you. This is from Virtual Species. I'll add a link in the description. They've solved this very, very well. So I'm going to quickly take a snippet of that and show that to you here, but also have a look at their page that shows how the Santa Fe problem can be solved with a genetic programming algorithm. Let's go. Okay, so here's the Santa Fe trail problem. So let's have a look. So initially, the movements of the ants are completely random. So they are not able to sense much of their environment, and they're pretty unsuccessful, as you can see. So the movement is random, but of course, that's the initial population. We start off, and they try to evolve, and some of them is a little bit more successful on finding food particles, and of course, it's these that's going to get mutated and cross over time so that we can find a better solution. So let's see what happens. So after 50 generations, there's a tiny bit of improvement. So the movement is not that erratic any longer, but of course, still very, very unsuccessful. It seems like it thinks that wrapping around and trying to cover all corners of the board will make it successful. But of course, there's only a certain number of executions that the program is allowed. So eventually, it will get to a point where it stagnates, and it can't find any more food particles within that set time. And of course, then something else will come about that improves. So let's see how this goes on. So after 150 generations, quite a bit of an improvement. So now you'll see that it almost stays on the entire path. Sometimes it strays off and then it comes back. What a wonderful implementation by Virtual Species. Head over to their channel as well. They've got some other things there as well. So it's always interesting to see what people have done to actually solve problems like these. But as you can see, maybe this one will get to the end. Let's have a look. I think it's right about here where it actually loses the trail. The other trail actually it goes back to that trail, and it just goes over and over. But of course, just a few generations later, at 175, the perfect solution was found. So yes, very, very good implementation by Virtual Species, which clearly demonstrates how a program can evolve. Here's the perfect program here on the side. That actually shows you. Okay, so that's a textual representation of the abstract syntax tree, but that's the recipe or the program that this little ant follows to actually follow the trail. And of course, it's reproducible. So you can take it on another path, and the same program should, in theory, also work for that application. And the only thing that drives this little ant, of course, is the fitness function. There was no other data that it was supplied with, and that is where the real power of genetic programming truly shines. A very, very good implementation by Virtual Species. Guys, and that's it. That's genetic programming. So thank you very much for joining. I hope you are going to have a look at our evolutionary programming, which is our next lecture. And I hope you find that interesting too. But thanks for watching up till now. Keep well and happy coding.